Howdy students, this is a video on Investigation 6, Experience 3. We're going to be looking at something called percent composition, empirical formulas, and not stated here, also molecular formulas. So let's take a look at the image here and what we see. A lot of times when you're buying fertilizer at the store, whether you know it or not, on the back they list out the relative percentages of nitrogen, phosphorus, and potassium. At different times of the year, your soil and your grass, they need different amounts of those three elements. And depending on what you buy, that could either hinder or stunt the growth of your grass. So you want to make sure that you're following those percentages very carefully. Now, what we're looking at here is what we call elemental abundance, and we're trying to figure out the relative percentages of each of the elements. So let's begin. The objectives today are to find and explain how to find, we are going to explain how to find the percent composition of a compound. We're going to develop models to illustrate the law of definite proportion and law of constant composition. We're going to find empirical and molecular formulas for a compound, and then we're going to use the subscripts within a chemical formula to represent a mole ratio. So let's start with percent composition of a compound. There is a formula that we want you to have in our notes. It is percent by mass of an element. So the percentage of an element equals, you need to write this down, the mass of an element divided by the mass of the whole compound times 100. So that's any percentage, right? Any percentage is part over whole. In this case, we're looking at the part of a specific element over the whole compound's mass. So let's practice. Find the percent composition for a compound that is formed from 28.0 grams of iron and 8.0 grams of oxygen. To do this, we first need the total mass of the compound. Okay, in this case, we're going to add the two masses together and know that the total of both elements combined is 36.0 grams total. We don't necessarily know if this is the molar mass. For now, it's just the relative amount of both elements. So what we're going to do is take the part of iron, and we're going to divide that by the total mass of both elements together. 28 divided by 36. We're going to multiply it so that we get a percentage out of 100 rather than 1. And we get 77.8% of iron. Now, there's two ways of doing this next part. You could do the same thing, or you could take the complement of this percentage. But we're going to go ahead and show you the work for the other part. We're going to divide 8 grams of oxygen, that's the part of oxygen, and divide it by 36.0 grams total. Multiply by 100, we get 22.2. You'll find that these are complements out of 100. They would both add up to be 100. If they don't, you've made a mistake. So if we're looking at percent compositions, a lot of times we can determine a compound based on its relative percentage of mass. So we know that if we found hydrogen in 11% abundance versus oxygen in 89% abundance, well, that's water, and that's what we call the law of definite proportions. No matter what, hydrogen and oxygen will always be in a ratio of 11 to 89 when it comes to mass. So let's do another one. Feel free to pause. Yes, this is longer, however, the same concept applies to this one. Let's go ahead and work it out together. Calcium acetate is Ca, C2H3O2, 2. We need a total mass, but nothing was given in the problem. So when in doubt, you use the molar mass instead of actual numbers in the problem. So calcium, there's one of those. Multiply by its molar mass on the periodic table, 40.08 equals 40.08. There are 4 carbons after we distribute that 2. 2 times 2 is 4. We're going to multiply by the molar mass of carbon, 12.01. Hydrogen, there are 6 of those, 3 times 2. We get 6.06. There are 4 oxygens at 64 grams. We're going to add all those together to get our total at 158.18 grams. This is the molar mass of calcium acetate. To find the relative percentages of each element, we need all 4, so there are 4 answers to this problem. We're going to divide each of the parts by the total mass. So check it out. Calcium, we're going to take that 40.08 and divide it by the total mass, 158.18. Multiply by 100, we get 25.34% calcium. We're going to do the same thing for each of those. Carbon, we get a percentage of 30.37%. Hydrogen, we get 3.83%, not a whole lot percentage. And then oxygen will make up our largest percentage at 40.46. Feel free to pause so you can copy this down. So let's do another one. Feel free to pause and try this on your own. Percent composition, we need the molar mass, so we're going to work through that. There are 4 oxygens. When we find the total, it's 158.0, very close to calcium acetate, believe it or not. This is potassium permanganate. We're going to divide each one by the total mass, multiply by 100, and find our percentages at 24.7, 34.7, and 40.5 respectively. So to answer the question, you would circle each of the percentages. So let's move on to our next part of the lesson with empirical formulas. The empirical formula, by definition, is the lowest whole number ratio of the elements in a compound. If you can simplify, then it's not an empirical formula. It may or may not be the same as the molecular formula, or what we call the real formula. So how do we do this? Well, in the e-text, it says that there are 4 steps. Number 1, find moles of each element. Then number 2, you set up a mole ratio. And then number 3, you would simplify that mole ratio by dividing by the smallest. And if your answers are not in whole numbers, we have to scale up or multiply by 2, 3, 4, or 5 to get whole numbers. Number 4, we would use the mole ratios as subscripts in the formula. If given percent composition, we can assume 100 grams of the compound. Now, those steps are kind of confusing. And in the e-text, they list out this diagram that walks you through percentages, mass, moles, ratios, and empirical formula. Well, we're not going to spend too long on this because we have a shorter version that we want to teach you. And we put it in the form of a poem, and it goes like this. Percent to mass, mass to moles, divide by smallest, and round till whole. Again, percent to mass, mass to moles, divide by smallest, and round till whole. We call this the happy clappy song sometimes. Let's put it into good use. A compound is 79.8% carbon, 20.2% hydrogen. Find its empirical formula. Percent to mass, mass to moles, divide by smallest, round till whole. So we're going to take percent and turn it into mass. We assume 100 grams of this substance. So the first thing you see here is that we've turned the percentages into grams, 79.8 grams of carbon and 20.2 grams of hydrogen. Percent to mass, mass to moles. Look at the next step. They converted mass into moles using our molar mass conversion. For carbon, 12.01 grams, and for hydrogen, 1.01 grams. Percent to mass, mass to moles. The next step, now that we have converted mass into moles, is to divide by smallest. The smallest amount of moles here is carbon at 6.64 moles. So we're going to divide each of these by the smallest number, 6.64. For carbon, it's 1. You'll always have one answer, that is 1. We call this the defined mole ratio. 20 divided by 6.64 gives us a value of 3. Percent to mass, mass to moles, divide by smallest, round till whole. Well, this is the point in time at which we could scale up if we needed to get things to line up. Well, we have exactly 1 and exactly 3, so we don't need to do that. And those numbers end up becoming the subscript. So there's 1 carbon for every 3 hydrogens. This is the subscript ratio in this compound. This is the empirical formula because we cannot reduce it any further. Feel free to pause and try this one on your own. Percent to mass, mass to moles, divide by smallest, round till whole. So percentages have been turned into mass on the far left. Masses have been turned into moles using the molar mass of magnesium, sulfur, and oxygen. Check your molar mass. We have moles, so we're going to divide by the smallest, which in this case is 0.957. When we do that, we get 1, 1, and 3. In this case, we don't have to scale up or multiply or do anything fancy. Those become the subscripts in our formula. So there's 1 magnesium, 1 sulfur, and 3 oxygens. This becomes magnesium sulfite. This is the empirical formula. So now let's look at the last portion of our lesson over molecular formulas. So molecular formulas are the real formulas or the actual formulas. They may be the same as the empirical or some kind of scaled up multiple. So take a look at the picture. We have methanol, which is CH2O. A derivative of methanol is ethanoic acid, which is C2H4O2. And you'll notice that is a scaled up multiple of 2 for methanol. And then another derivative would be glucose, actually, which is C6H12O6. This would be a 6 times factor of methanol. So how do we find the molecular formula? Well, there's a small equation we need to know. You need to write this in your notes, but we're going to find that multiple, that scalar value, by taking the molar mass and dividing it by the empirical formula mass, which we call the EFM. So the equation is pretty short. It's the multiple is going to equal the molar mass, or what we call the GFM, and divide it by the EFM. So take a look at the diagram here, the chart. Formula name, if it was CH, the molar mass of that empirical formula is 13. But if we have something like C2H2, like ethyne, the molar mass is 26, which we know is a scalar value of 2 times the multiple. C6H6 is benzene. That ends up being a molar mass of 78, which if we divided it by 13, we would find that it's 6. So we're going to multiply each subscript in the empirical formula by the scalar value, to get the molecular. So what does that look like? A white powder is analyzed and found to have the empirical formula of P2O5. The compound has a molar mass of 283.9 grams. What is the compound's molecular formula? So in the problem, it tells us that the molar mass of the real formula, the actual formula, is 283.9 grams. We have the empirical formula, so let's first find the molar mass of the empirical formula. Well, here it is. 2 phosphorus, 5 oxygens gives us 142.0 grams per mole. If we take our equation, which is N equals GFM over EFM, or molar mass over EFM, we're going to divide the 283 by the 142. And when we do that, we get a value of exactly 2. We're going to take that value of 2 and scale or multiple the P2O5 by multiplying the whole formula by 2. We get P4O10. This is the molecular formula. Okay, last problem. We're going to combine empirical and molecular formulas. This is a lengthy problem. You will need space to write this out. A compound is used as an additive for gasoline and has the following percent compositions: 71.65% chlorine, 24.47% carbon, 4.07% hydrogen. The molar mass of this compound is known to be 98.96 grams. Determine the empirical and molecular formulas. So we have to do 2 things here: empirical first, molecular second. Empirical: percent to mass, mass to moles, divide by smallest, round till whole. So let's do that. Percent to mass, we're turning the mass of chlorine into moles of chlorine. Percent to mass of carbon, we're turning the mass into moles of carbon. Percent to mass, we're turning the mass of hydrogen into moles of hydrogen. After we divide, we get moles of each. Percent to mass, mass to moles is complete. Divide by smallest, 2.02. We're going to get 1, 1, and 2. So the empirical formula is ClCH2, 1 chlorine, 1 carbon, 2 hydrogens. This is the empirical ratio. We're not done though. Now we got to find the molecular formula. Well, we need to find the molar mass of this empirical formula. So there's 1 chlorine, 1 carbon, 2 hydrogens. So this is our normal molar mass, nothing special here. The empirical formula mass is 49.5 grams per mole. We're going to take the actual molar mass in the problem, 98.96 0.96 and divide it by the 49.5. We get a ratio or a scalar value of 2. We're going to scale up our empirical formula to get our molecular. So the molecular formula is twice or double the empirical.